Hi, this is Brandon Rohr with How Decision Trees Work. Decision trees are one of my favorite models. They're simple and they're powerful. In fact, most high-performing Kaggle entries are a combination of XGBoost, which is a variant of decision tree, and some very clever feature engineering. The concept behind decision trees is refreshingly straightforward. Imagine creating a data set by recording the time you left your house and noting whether you arrived at work on time. Looking at it, you can see that for the most part, departure times before 8:15 result in punctuality, and departure times after 8:15 result in tardiness. You can summarize this pattern in a decision tree. The very first branching point is the question, did departure occur before 8:15? There are two branches, a yes and a no. For consistency, we'll keep all of our yeses on the left. Placing this decision boundary divides the data up into two groups. And although there are some stragglers and exceptions, the overall pattern is captured by placing this decision boundary at 8:15. If you depart before 8:15, you can be reasonably sure of getting to work on time. And if you depart after 8:15, you can be reasonably sure of being late. This is the simplest decision tree possible, a single branch. We can refine our estimate of punctuality by subdividing both the before 8:15 and the after 8:15 branches. If we add additional decision boundaries at 8 o'clock and 8:30, then we can divide up our arrival estimate more fully. Those before 8 o'clock are confidently on time. Those between 8 and 8:15 are probably on time, but not guaranteed to be so. Similarly, departure times after 8:15 can be divided into those after 8:30, which are almost certainly late, and those before 8:30, which still have a small chance of being on time. This decision tree has two levels. Decision trees can have as many levels as you want. Most often, each decision point or node has only two branches. This example has a single predictor variable and a categorical target variable. The predictor variable is our departure time, and our target variable is our punctuality, whether or not we're late. Because it has only two distinct values, it's categorical. Decision trees with categorical targets are also called classification trees. We can extend this example to the case where there are two predictor variables. Consider both the departure time and the day of the week. We'll start counting at Monday equals 1, so Saturday equals 6 and Sunday equals 7. Inspecting the data, we can see that on Saturday and Sunday, the green filled donuts, representing being late, extend further to the left. This means that leaving at 8:10 is probably sufficient to get you to work on time on a weekday, but probably not on the weekend. To represent this in a decision tree, we can start as we did before by putting a decision boundary at 8:15. Any departure times after 8:15 are likely to be late. Departure times before 8:15 are inconsistent. Before, we assumed that they would be on time, but now we can see in the data that that's not entirely true. To make our estimate better for the weekends, we can subdivide the before 8:15 departure times into weekday and weekend. Now, a weekday departure before 8:15 is confidently on time. However, weekend departures before 8:15 are mostly on time, but not entirely. We have updated the decision tree with a node that reflects this new decision boundary. Now we can further refine our estimate by subdividing our weekend pre-8:15 departure times into before and after 8 o'clock. Before 8 o'clock, almost all of the arrivals are on time, and between 8 and 8:15, the majority of them are late. Now we have our two-dimensional decision tree neatly divided into four regions. 2 of them reflect on-time arrivals, and 2 of them show late arrivals. This is a 3-level decision tree now. Note that not all of the branches need to extend down to the same number of levels. Now we can look at an example with a continuous target variable rather than a categorical one. When a model is used to make predictions about continuous numerical variables, it's also called a regression tree. So far we have looked at 1- and 2-dimensional classification trees. Now we'll look at regression trees. Let's consider the question of what time someone wakes up, as predicted by their age. The root of our regression tree is an estimate for the entire data set. In this case, if you had to make an estimate without knowing someone's age, a reasonable guess would be 625. This is the root of the decision tree. A reasonable first split is at age 25. On average, people younger than 25 wake up at 7:05, and people older than 25 wake up at 6 o'clock. There's still a lot of variation in the younger group, so we can split it again. Now the people younger than 12 can be estimated to wake up at 7:45, and people between 12 and 25 can be estimated to wake up at 6:40. The over 25 group can be meaningfully subdivided too. Those between 25 and 40 wake up on average at 6:10, and those between 40 and 70 wake up on average at 5:50. There's still a lot of variation in the youngest group, so we can further subdivide it. By slicing again on age 8, we can refine the estimates to more closely fit the data. We can also subdivide the 40 to 70 group on the 58-year line. Notice that we are getting to where we only have 1 or 2 data points per leaf of our tree. This is a dangerous condition and can lead to overfitting, which we'll talk more about in a minute. The resulting tree lets us make a numerical estimate depending on someone's age. If I need to estimate the wake-up time for a 36-year-old, for instance, I can start at the top of the tree. Are they younger than 25? No. Go to the right. Are they younger than 40? Yes. Go to the left. The estimate then becomes 6:10 a.m. The structure of the decision tree lets you sort people of any age into their respective bin and make an estimate about their wake-up time. We can also extend this regression tree example to have 2 predictor variables. If we consider not only someone's age, but the month of the year as well, then we can find even richer patterns. In North America, days are longer in summer months, and it gets lighter earlier in the morning. In this completely unrealistic example, children and teens are unburdened by the rigorous schedules of work and school and have their wake-up time driven by when the sun comes up. On the other hand, adults fall into more regular patterns, fluctuating only slightly with the seasons. Again, older people in this example tend to wake up a little earlier. We construct this decision tree much the same as the last one. We start with the root, a single estimate that roughly fits the entire data set, 6:30. Then we look for a good place to put a decision boundary. We split the data on age 35, creating 2 halves, one for our under 35 population with a wake-up time of 7:06, and one for our over 35 population with a wake-up time of 6:12. We repeat the process, subdividing our younger population on whether it is before or after the middle of September, and whether it is before or after the middle of March. This isolates the winter months from the summer months. Winter months have a wake-up time of 7:30 for those under 35, and in the summer months it's 6:56. Then we can revisit our over 35 population and split them again on age 48 to get a more accurate representation. We can also go back and subdivide our under 35 winter wake-up times on age 18. Someone under 18 in the winter will wake up at 7:54 as opposed to 6:48 for those over 18. You can start to see the emergence of the tall corner peaks. As we make each additional cut, the shape of our decision tree becomes a little bit closer to that of the original data. Also, you'll notice in the upper right-hand plot that the decision boundaries begin to slice the dataset into regions of approximately uniform color. The next cut continues this trend, focusing on dividing those younger than 35 in summer months to those older and younger than 13. The shape of the model becomes even more similar to that of the data. You can imagine continuing this process until the model closely represents the smooth trend underlying the data. Each decision region would become progressively smaller. The approximation to the underlying function in the data would become progressively better. The power of decision trees is not without pitfalls. An important one to watch out for is overfitting. Returning to our example of a single variable regression tree, age versus wake-up time, imagine that we continue to make cuts on the age axis until there were only 1 or 2 data points in each bucket. When we get to this point, the decision tree explains and fits the data very well. It fits too well. Not only does it capture the underlying trend, the smooth curve that the data follows, but it also catches the noise, the unmodeled variation that's included in the measured data. If we were to take this model and use it to make predictions about new data, the noise from the training data would actually make our predictions less accurate. Ideally, we want a decision tree to capture the underlying trend, but not to capture the noise. One way to safeguard against this is to make sure that there are more than a handful of data points in each leaf of our decision tree. That way, any noise will be able to average itself out. Another thing to watch out for is having lots of variables. We started with a one-dimensional regression tree, then included month data to create a two-dimensional regression tree. Decision trees don't care how many dimensions we have. We could, for instance, also add latitude, the amount of exercise someone gets on a given day, their body mass index, and any other variables that we think might be relevant. To visualize this, we'll use a trick shared by Geoffrey Hinton, a renowned deep neural network researcher. He recommends, to deal with hyperplanes in a 14-dimensional space, visualize a 3D space and say 14 to yourself very loudly. The challenge when working with many variables then becomes deciding which variable to branch on when growing our decision tree. If there are very many variables, then this can require a lot of computation. Also, the more variables we add, the more data we need to reliably choose between them. It's easy to get into a position where the number of data points is comparable to the number of variables. When our data set is represented as a table, this manifests itself as the number of rows being comparable to the number of columns. There are methods for dealing with this, such as randomly selecting a variable to divide on at each branch, but it's something to keep an eye out for and handle mindfully. As long as you keep your eyes open for places where decision trees might fail, you're free to take advantage of their strengths. Decision trees are fantastic for when you want to make as few assumptions about your data as possible. They're quite general. They can find nonlinear relationships between your predictor variables and your target variable, as well as nonlinear interactions between predictor variables. Quadratic, exponential, cyclical, and any other relationships can all be revealed as long as you have enough data to support all the necessary cuts. Decision trees can also find non-smooth behaviors, sudden jumps, and peaks that other models like linear regression or artificial neural networks can hide sometimes. There's a good reason that decision trees consistently outperform other methods on data-rich problems. Thanks for tuning in, and I hope this is helpful in building your next project.